Bayesian optimization enables global optimization of expensive multimodal objective whereby an acquisition function trade-off exploration and exploitation. Bayesian optimization has many applications including automatic scientific discovery, automatic machine learning and hyperparameter tuning, and automating and engineering control. However, unlike most optimization procedures, Bayesian optimization typically does not derive information, and we can imagine such information might be quite useful. If we want to help our friends in scavenger hunt, we might say look in that direction and look in this direction, and hopefully they find what they're looking for more quickly. This paper is focused on how the best use of derivatives information to help Bayesian optimization find what it is looking for and more quickly. Key ideas of the paper. Gaussian process are often used to model or objective function in Bayesian optimization. Unfortunately, Gaussian process regression naturally accommodates derivative observation. Left figure. Gaussian process distribution for objective observed over the location represented in blue dots. The predictive GPR is given by the black curve and the predictive uncertainty is given by the shade. In the figure on right, we have also condition to the derivative observation, and we can consider this distribution over objective significantly updated. However, it readily matters to the use of the derivative in Bayesian optimization. In the bottom row left, we have exactly the same figure on the previous slide before we observed derivatives. In the bottom row middle panel, we have two different acquisition functions, EI in green and KG in red, showing the max value point of Q in the next optimization. Trading of exploration where GPR has high predictive uncertainty and exploration where it has a low predictive mean. In this case, both of this acquisition function KG and E are proposing similar equivalence. However, over the top row, after we observe the derivative, we see the KG is proposing the very different point where E is relatively unchanged, and we'll see this is because KG is anticipating the value information in the observing radiator at the next time step. Imagine we have Gaussian process distribution over the subjective that we were trying to optimize, which we have observed by the points given by the blue dots. In the bottom figure, we have our acquisition function which creates exploration going through the GPR, high predictive uncertainty shown in the shade, and exploration going through as low predictive mean in order to propose the next act. In particular, here we have expected improvement, EI the popular acquisition function which maximizes the expected difference between our objective based point and the current objective. Here EI is telling us to propose the next point of location on the red box, which we do. When we do that, we update our positive over objective and update acquisition function. Now EI is proposing to move to location of this red box. Again we will update our posterior position, and we can continue until EI says it. EI decisions are almost unchanged by the gradients. However, we say early popular acquisition function are necessary that responsible to the presence of derivative information. Imagine we take n sample of the function and it is a gradient. From this sample we computed the posterior distribution, and In the posterior distribution, we have posterior mean indicated here a solid black line with the notation mu n of x. Report solution for optimization function. We would choose the point with lowest posterior mean and value at the point is mu star of n. If we take q additional samples of value in the function, its gradient points, we would have new posterior means and new minimum value, and we write it as mu star n plus q. The difference in these two minimum would be the value created through sampling. Our acquisition function is the expected value of this reduction computed law. We call it as DKG factor, and this algorithm samples at the point maximizes this acquisition function. Here is the way to calculate the acquisition function. Now, while we could optimize the DKG acquisition function, we can directly use the evaluation method coupled with derivative-free simulation-based optimization method. Instead, we do something that is more specific method instead and more computational. We use multi-stat stochastic gradient, where the stochastic gradient is developed using new ideas. The first idea is indefinite as test-based analysis. This lets us extend the gradient and the expectation operator that defines the gradient of the acquisition function. It tests use extends to write the gradient as expectation of the gradient random function. If we can officially sample this gradient function, that will be unbiased estimator then use inside of stochastic gradient. Second idea is to develop envelope theorem. Envelope theorem allows us to compute this inner gradient artificially. This quantity is the gradient of the minimum of the posterior as the function of exhaustion noise for stimulator and same. As we change where we sample the implicit inside of gradient operator, the location that minimizes the posterior manages. What the envelope theorem tells us is that actually we can ignore and take the minimized to fix the each replicated issues. That solves the significant issues and effort. It means we only need to minimize the posterior ones for simulation replicated. In addition to this land of quantitative analysis, theoretical work proves that DKG algorithm is consistent in the since that is the limit as you take the infinite number of samples and function on have a infinite feasible domain that the solution to the acquisition problem you get using knowledge gradient, and the acquisition function verges the blue block of the acquisition function. DKG is also flexible. We can incorporate biased gradient observation using ideas from multitasking observation, optimization, and incomplete gradient observation. Derivatives make the Bayesian optimization much faster as long as we use the right acquisition function. There are three obstacles using derivatives in Bayesian optimization. First, the ability to measure derivatives. Second, expensive measuring derivatives. Third, expensive Gaussian process. In future, we can observe a time of Bayesian optimization with gradient is applicable to inexpensive objective where standard gradient based optimization are used to do with faster convergence and robustness to multimodality.